Hi, I'm Shreya and this is Mikayla, and today we'll be talking about speech processing. So why is speech processing important? First of all, it has a lot of direct use cases. It helps in bridging language gaps. For example, if I cannot speak in Chinese and Mikayla can only speak in Chinese, then I can understand her by the use of a speech processing tool. Furthermore, it can aid people with disabilities. For example, people with speaking disabilities as well as hearing disabilities can use such tools to function normal in life. It can also be used for therapeutic purposes. A lot of people now prefer talking to machines in times of anxiety so that they do not have the pressure to talk to a real human. It also helps in making machines smarter. You can now provide input to machines in a multimodal setting. This was in fact not possible if you only wanted to input text. For example, the difference between yes and yes could not be identified previously. It is also that speaking is much faster than typing, and this is preferred by a lot of people because of that. So speech processing in fact lies directly at the intersection of linguistics, computer science, and electrical engineering.
So just to give you guys a background about some of the research that has happened in speech processing over the past century. So the first major breakthrough in speech processing was that at Bell Labs in the 1950s, there was this machine called Audrey, which was able to recognize spoken numbers from 0 to 9. So one problem with this was that the machine was very susceptible to changes in accents, changes in ways of speaking. And it was actually much better at recognizing what the inventor spoke than what the participants said. And of course, being a pioneer in AI research, CMU was also involved in speech processing early in the entire frame of things. So in the 1970s, CMU actually worked on a DARPA-funded project called Heartbeat. And what Heartbeat does is that it had a vocabulary of about 1,000 words, which was a lot at that time. And it was the first machine which was actually able to recognize full sentences. So the problem of there being different accents and different ways of pausing between words was still a pretty big problem for Heartbeat. So just to give you guys an example, for example, if someone said euthanasia, this could easily be confused with youth in Asia. And the reason for this is because before the advent of machine learning and everything, before the 1990s, many speech processing systems were based on template matching. And so if you have a template for example, euthanasia, youth in Asia, because it sounds similar, would probably be template matched to euthanasia. And so just to give you guys an idea of some recent advances in speech processing research, something that's very popular right now and has achieved state-of-the-art is called sequence-to-sequence models. So sequence-to-sequence models were first invented at Google in 2014, and since then they have fine-tuned it a lot. And the way a sequence-to-sequence model works is that there's an encoder which takes in some inputs, and after that it maps it to some feature embedding, and after that it passes it to the attention, which has a sort of memory. So it's able to recognize which parts of the features are important. And after that, this is passed to a decoder, which will be able to generate for example, text, or maybe it could be used for translation and things like that. Some current research directions which are kind of trending in this field right now are universal speech processing. So the idea of universal means that a single machine can be used for speech processing tasks for all languages. And this is actually pretty important because there are quite a lot of languages which don't have many speakers and are dying off. So it would be really useful if we could apply transfer learning and use, for example, our data in English to understand something that's in some dialect which is pretty obscure and doesn't have many speakers currently. And another thing that people are doing are reducing bias. So what reducing bias means is that when we feed text into our speech processing tools in order to train them, because these texts come from our daily lives and things like that, so there's a lot of implicit biases in them. If you look at a table on the left, you could see some biases that tend to be learned by the model, such as black equals homeless and Asian equals laborer. And obviously these things are not something that we want our speech processing models to have. So researchers are figuring out how to normalize the bias in word embeddings.
Currently, the research at CMU involves all of the fields that could be developed from speech processing. For example, a lot of professors are working on development of algorithms that can be used on different speech processing applications to improve the accuracy of this model. Furthermore, a lot of professors are working on voice production, which is basically trying to make the machine sound a lot more like human. And FestWorks is an example of such a project. We are also trying to identify the real world applications and basically developing software that can be implemented in the industry. A lot of work has also been done to identify the social benefits of speech processing, for example, globalization or helping the economically weaker section by the use of speech processing. During the course of this project, we talked to Professor Alan Black, who is a leading professor at the Carnegie Mellon LTI group, and he is currently working with a project called code switching. So, as a lot of bilingual speakers are aware, we tend to change the language that we talk in when we're talking to a fellow person who is also bilingual. For example, I being a bilingual in English and Hindi can normally easily switch languages from English to Hindi when I'm talking to a similar person. And this is an important aspect of casual talks. And therefore, a machine needs to identify when the person switched languages and the point at which the person switched languages. And thus, this can also decrease the amount of similarity of the sentence structure and things like that. And this is like a leading field where research needs to delve into to make machines smarter. Now, the basic difficulties in research are the evaluation of the result. A lot of the participants have innate biases. For example, if you like the Scottish accent a lot and the bot talks in a Scottish accent, you might just have a positive bias towards the bot and tend to evaluate it to a higher degree as compared to a bot that doesn't. The unsolved problems and the future directions would first of all be detecting the noise in the input and discarding it. For example, if I'm talking to you and I suddenly talk to Alexa and you talk back to me, the Alexa device needs to identify which of the inputs it needs to listen to and which input it needs to discard. Furthermore, we also need to add more prosthetic features such as pauses, stresses, and intonation to make the machine feel more human-like. Furthermore, we can also make the human-machine interaction more friendly and smart by customizing it to individuals so that the person can relate to it more. A lot of security concerns have also arisen because sometimes the input is not actually given and the machine might just say call a policeman when it's not needed.